Okay, so let's remember back from pre-cal and algebra 2, this idea of an inverse. So the two most basic inverse functions is your e to the x function and your natural log function. Okay, so those are our two quintessential inverse functions. And they are reflections over the line y equals x. Now, in pre-cal, you should have done something called function compositions, where you proved that a function g is the inverse of a function f, if and only if f of g of x or g of f of x, both of those function compositions equaled x, okay? And we learned in algebra 1, excuse me, not in algebra 1, in algebra 2 and in pre-cal that we call f inverse, we use that as our notation for f inverse, okay? So some things that you should know about inverses. Number one is that if g is the inverse of f, then f is the inverse of g. They're inverses of each other. One is the inverse of the other, okay? The domain of f inverse is the range of f, and the range of f inverse is the domain of f. So basically, in short term, in the easiest way to explain that is their domain and their ranges switch, okay? It's also important for you to know that not every function have an inverse, but if a function does have an inverse, that inverse is unique, okay? Let's do a really, really basic example. Given the function f of x is the square root of x minus 1, find the inverse. So let's think back into algebra 2 when we learned how to find an inverse. Step 1 for finding an inverse is that because it's a reflection over the line y equals x, first off, I'm going to write y equals the square root of x minus 1. So I'm just copying my function down using y instead of f of x. But step 1 was that you switch x and y. Step 2 was that you solved for y. So if I want to get rid of the square root, I'm going to square this and get y by itself, and I get x squared plus 1 is equal to y. So instead of the terms y, we're actually going to say that this is the inverse function. So that means that f inverse of x is equal to x squared plus 1. So there's part A, we found our inverse. Part B, we want to graph these two inverses on the same set of coordinate axes. Now, when we go to graph this square root function, you need to know that's a square root function shifted to the right 1 unit. So there's my square root function. Now the other one, you may be looking at it and going, hey, I'm just going to graph a parabola. But we're not just going to graph a parabola. Normally, we would graph a parabola 1 unit up and we'd have both sides. But this other half over here, we're actually not going to graph, okay? So the reason we're not going to graph that is because we need to consider our domain and range of these functions. First off, recognizing that these are indeed a reflection over the line y equals x. But let's talk domain and range. Part C. My original graph, my original function f, had a domain of x is greater than or equal to 1 because my square root function was defined for 1 and up. Its range was defined for y is greater than or equal to 0. But when I go to write my domain and range of my inverse function, remember that their domain and their ranges are going to flip. So that means that this range becomes my domain. So this is now going to be x is greater than or equal to 0. And my domain becomes my range. So this is y is greater than or equal to 1. And if we look at my graph, this should make sense. I only want to take the positive part of this graph. I didn't take the negative part of this graph. And sure enough, the range is defined for greater than or equal to 1. So at its basic level, to find an inverse, we switch x and y, and we solve for y. Okay? But how does this apply to calculus? Okay? So let's do a real quick exploration. Here are two functions. I have f of x equals x cubed, and its inverse, the cube root of x. Now, I'm not going to go through the process of proving that those are inverses. You should know that. You can prove it on your own. Switch x and y, solve for y. Okay? So let's get some basic information. Number one, f of 2. I'm going to plug into my function and say, hey, what's 2 cubed? Well, 2 cubed is 8. Okay? What would f prime of x be? Well, f prime of x would be 3x squared. And f prime of 2 would be 3 times 2 squared, or 12. Okay? Well, what about f inverse of 8? Now remember, f inverse of 8 means I'm plugging into my inverse function. So what is the cube root of 8? And it's 2. And big, giant, flashing light bulbs need to be going off, because you see that at this point, f of 2 was 8. F of 2 was 8. F inverse of 8 is 2. And that should make sense, because x's and y's are flipped for my inverse function. Okay? Now, next thing it asks me to do is to find the derivative of my inverse function. Find the derivative of my inverse function. Now, put a big star next to this. The notation we're going to use for the inverse of the derivative, or the derivative of the inverse, is f inverse prime of x. Now, the reason why we put x in parentheses is not because it's being multiplied. It's because we don't want you to confuse that we're taking the derivative of the inverse. And it's just weird notation. But when you read this, you need to be reading it as derivative of the inverse function. So what is the derivative of my inverse function, cube root of x? Well, it's important to remember that that is x to the 1/3. So my derivative would be 1/3 x to the negative 2/3. Okay, let me write that a little bit nicer. To the negative 2/3. So then what would this be if I plugged in 8 into this? 1/3 8 to the negative 2/3 power. And here's where I know you guys struggle. So what does this actually mean? 3 times 8 to the 2/3 power down here. Now, 8 to the 2/3 means that I am going to, and you could plug that in your calculator if you wanted to, but this 8 to the 2/3 thing right here means that I'm going to take the cube root of it and square it. The cube root of 8 is 2, 2 squared is 4, and we get 1/12. Now, some really important things happen here. Number one, look at f prime of 2, and look at f prime of my inverse of 8. They're related. In fact, they are reciprocals of one another, and that's going to be super important. I want you to write yourself a note. Hey, they are reciprocals. Okay? So that brings us to a theorem, a really important theorem. Okay? Okay, so here it is. The derivative of an inverse function. If you want to find the derivative of an inverse function, which is important for you to know that, number one, the derivative of my composite function, I don't know why I just crossed through that. The derivative of my composite function can't be equal to 0, and g prime of x is 1 over the composite function. This is the part where you need to know. If I want to find the inverse's derivative at a value a, it's going to be equal to 1 over the derivative of the inverse at a, okay? And basically, in short and easy terminology, it's going to be the reciprocal of the derivative, okay? So let's do a real quick and easy example. We'll do a couple of them, and hopefully you guys will get this. It's so easy, okay? So here's what it tells us. F of 3 is 5, F prime of 3 is 7 halves, and it wants us to find F inverse's derivative at 5, okay? So step 1, it's important for you to know that if this is my x and y, that the following is true. The inverse value of 5 is 3. The inverse's value of 5 is 3. And all I did is say, I'm going to switch x and y, okay? So now, using my formula, if I want to find the derivative of my inverse at 5, it's going to be 1 over the derivative of the inverse of 5 which is 1 over, we know that the inverse of 5 is 3, so it's going to be 1 over f prime of 3. And guys, this should make sense. You take the reciprocal of the derivative. So here, I know that that is 1 over 7 halves. So my answer is 2/7. So at its most basic level, this is how we're going to use it. Okay, let's do like 2 more. Okay. In this one, I didn't give you a function value. In this one, I gave you a function and I asked you to find the inverse's derivative at 2. Here's what we need to do. Step 1 is, let's go ahead and find the derivative. So my derivative is going to be 3x squared plus 2. Okay? I need to find the derivative. I got ahead of myself, guys. I'm sorry. Okay? Now, in order to answer this question, I need to know what is my function value that gives me 2? What is my function value that gives me 2? My original function value. So if I set my original function equal to 2, sorry about that, guys. I had to let my dogs out. So I want to know, where does my original function equal to 2? Now, the reason I need to figure out where my original function equals 2 is because I want to find the derivative of my inverse at 2. So in order to do that, I'm going to be using the reciprocal of the inverse value. So where does my function equal 2? Now, you can use a calculator and determine that at x equals 1, and sure enough, you could plug that in. 1 cubed is 1 plus 2 times 1 would be 3, and then 3 minus 1 would be 2. So x equals 1 gives us that value. So here's what you know. f of 1 equals 2. That tells me that f inverse of 2 is equal to 1. So basically, I can find that function value on my inverse graph. So if I want to know the derivative of my inverse at 2, my rule says 1 over f prime of f inverse of 2. So we just established f prime. This value is 1. The inverse of 2 is 1. So all I have to do is find my derivative plugged in at 1. Okay? 3 times 1 squared plus 2. And I'm going to get 1/5. 1/5. Okay? So let's do one more, one last one. Let g of x equal the square root of x plus 1. Find the derivative of the inverse at 2. And that's exactly how I'm reading this. Derivative of the inverse at 2. Okay. Step 1. Find your derivative. Because you know you're going to need it anyways. So if I find my derivative, keeping in mind that this is going to be x plus 1 all to the 1/2, my derivative will then be 1/2 x plus 1 to the negative 1/2 power. Okay? Now here's what you need to ask yourself. If I want to find g inverse derivative at 2, I need to know, where is my function actually equal to 2? Where is my function actually equal to 2? Okay? So to do that, I'm going to say 2 is equal to the square root of x plus 1, my original function. I'm going to square both sides and get 4 is equal to x plus 1. Subtract 1, and we find that x equals 3. Now, here's what that tells us. That tells us that g of 3 is equal to 2, which means that g inverse of 2 is equal to 3. And the reason why that's important to know is because my formula for the derivative says if I want to find the derivative of the inverse, it's going to be 1 over the derivative of the inverse at that point 2. Okay? So now we've established that the inverse of 2 is 3. So I'm going to do 1 over g prime of 3. Okay? So this point, you have to find that point. And you find that point by setting your original equal to the function value you're trying to find the inverse of. And guys, I know that's like extremely weird to think about. So now I'm just going to evaluate my derivative at 3. So down here in the bottom, I'm literally saying 1/2 3 plus 1, and this one ends up being kind of cool. One half. My stylus has been sucking lately. 3 plus 1 to the negative 1/2 power. Now be careful, if I have a negative exponent on my denominator, that actually is going to take this and move it up to the top. But if you're not convinced, here's what's going to happen. 1 over 2 square root of 4 which is 1 over 1/4. we're in a final answer of 4. Okay, now I'm not going to do the trig derivative at the very bottom, but the last thing that I want to talk about is this idea of even and odd functions. This idea of even and odd functions. Okay, you guys did this in pre-cal, so this is going to be a really quick review. An even function is where your function, when I plug in negative x, is completely equal to your original function. And the way that I would give you a real quick example, basic example, is x squared. So if I think about x squared, here's a point. This point would be positive x and f of x. And over here, symmetric would be negative x, and it has the exact same y value. So when I plug in a positive x or a negative x, they share the exact same y value. Now, an odd function is a function where when I plug in negative x, I'm going to get negative f of x. So the most quintessential odd function is x cubed. And if I think about some points on my x cubed graph, here is a point x and positive f of x. And here is a point down here, negative x, and his y value is the same, but just negative. Okay? Now, some things that you should know. Sine is an odd function. If I plug in negative x, it is equivalent to the negative y value. But cosine is an even function. And this should make sense to you if you think about the graphical pieces. So my sine graph looks like that. It is an odd function. My cosine graph is symmetric. So when you see even, I want you to be thinking about symmetry over y. And an odd function is symmetry over y equals x. Now in calculus, really where it comes in handy is you need to be able to determine if something is even or odd. And to do that, you're going to plug in negative x everywhere you have an x, use your properties of exponents or trig to simplify. If your resulting function is the same, we say that that function is even. If the resulting function switches all of your signs, then we say it's odd. If it doesn't match your original or it doesn't change sign, then we say it is neither. And you did this in pre-cal. So if you wanted to know if this function x to the fourth minus 3x squared plus 7 is even or odd or neither, step 1, everywhere you have an x, we're going to plug in negative x. So I get negative x to the fourth power minus 3 times negative x squared plus 7. Now let's use our properties of algebra. If I'm going to raise a negative number to an even exponent, that's going to become positive. Same thing happens right here. A negative exponent to an even power, again, makes that positive. And my original function matches my resulting function. So therefore, f of x is even because my function did not change. Okay? The next one, I'm going to do the same thing. I'm going to plug in negative x everywhere I have an x. So we're going to use our properties of algebra. If I have negative x raised to the fifth power, that is going to stay negative. So all my signs were originally positive. Now all my signs are now negative. Every single sign flipped. every single sign flipped, so therefore this is an odd function. And the very last one, everywhere I have an x, I'm going to plug in negative x. I was trying to use color and then I just gave up. All right, so let's do this. If I plug in negative x everywhere I have an x, starting with this, I have negative x to an odd power, which will stay negative. So negative 2x to the third. So that sign changed. To the next one, I have a negative x squared. That's going to become positive. So plus 4x squared. And then my next one says negative 7 times negative x. That's going to become plus 7x. And then my 1 is still hanging out on the outside. So let's look at my original function. Did all the signs change? Some of them changed, but not every sign changed. And in order for this to be an odd function, every sign would have to change. So therefore, this one is neither. And that's it, guys.